Okay, welcome to part 8 of our Scaling AI series. In this video, we're basically just going to give an update on the work we've done to date, some changes in the way that we've approached it, and as usual, we'll attach the code as of this video in the description below, so you can just go ahead and download the plugin and explore it on your own. So there's a number of changes that we've done since our last video, mostly coming out of testing, debugging, performance tuning, etc. So let's take a walkthrough of that first. So here's the changelog. The first thing we did was we got rid of the somewhat annoying experience that was counting down for other players to join, having the scoring widget at the top of the screen. So we basically stripped that out of our open world experience. It was quite easy to do. I'll show you exactly where you can change it in your own experience. That was just more of a quality of life. If you've watched the previous videos, you'll know why. Then what we had to do is in testing, we realized that our assumptions around replication between client and server were not holding true. So we stepped back and rethought how we were sending data back and forth between the client or the server and the client, and ended up with this approach, which we'll explain a little bit more, but basically replicating the cached pawn info upon wake up and sleep. So that's only replicated when the AI is awoken or put to sleep. The target yaw when we rotate. So we replicate the float variable target yaw now when we rotate the character. And then we have two multicast events, one for the sound effect and one for the anim montage. Those needed to be done through multicast, and we'll talk about why in a few moments. We've since added our nameplate component, which allows us to show a nameplate optionally above an AI, whether it's for interacting like a crafter or a quest giver, or for a mob, so with or without health bar. We can talk through that in a few minutes. We stripped out the collision sphere. We're not using it. None of our videos have used it so far. We do still intend to use it, but for cleanliness, we just pulled it out for now, so it'll likely make its way back in later. There's a new AIPawn movement component, which basically extends the floating pawn movement component and allows us to simulate the proxies for smoothing. We'll show you kind of with and without that, so you see why it's necessary. And then we pulled out, we were experimenting with the common conversation plugin, which in 5.1 was a beta experimental framework for enabling conversations, which we thought might be promising. However, as it so happens, this month in the marketplace, there is a free asset that appears to do much of the things that we were going to consider with the common conversation plugin. So we'll play with the free asset for a little bit and see how far we get with that. We may come back to the conversation plugin. However, there isn't a lot of documentation on that plugin. It isn't well fleshed out at this point. So it's probably best that we shelf it at this stage and come back to it later. So the first thing to stop the sort of match event in open world, basically you just go into your experience definition, your Lyra experience definition, and you'll note that there's this team deathmatch scoring, or you may have a different scoring, but this scoring component that is added is what's causing the changing of the phases. And if you watched our 3v3, we created our own 3v3 scoring and replaced this with our 3v3 scoring. So for open world, we've gone ahead and created this no scoring, where instead of doing a pre-match, match, post-match, and controlling which team is getting points and scores, etc., we've just created this very simple no scoring. And then that allows us to use that one in scenarios where we want to be in a level but not have a sort of scoring mechanism operating. And it's very simple. So no scoring. Basically, we stripped out all of the functions on begin play. Once the experience is ready, we simply push ourselves into the playing phase, and that's it. We have nothing on phase end. We basically have stripped out all the scoring logic, all of that, and basically just That's it. The other thing you'll need to do is remove the scoring widget. So depending on where your ability sets are, somewhere in that structure, you're adding the team deathmatch scoring widget to the UI. You can just go ahead and find that and remove it, and then that'll take it out of your open world experience. So that's it for that one. If you download the code and you take a look at the C++, based on all of our testing, there's basically these 5 functions that are now in the AIPawn, and they are responsible for communicating to the client when we're doing things on the server. So if you remember, the AI spawner is a server-only component or actor, and all of our AIs function on the server, and then that information will be sent to the various clients. And so the way we're sending that is through these various activities. So on our rep of pawn information, we send the bulk of the data across. That is on activation or on sleep. So that's done kind of only once when the pawn is brought in, so it doesn't have a big performance hit in gameplay. When we play audio or play a montage, we're using this multicast event. And the reason we're using the multicast from the script fragment is that multicast is sort of, if you're not in the net relevant range, it just doesn't happen for you. So if you're halfway across the map, you don't need to receive this multicast. It's also sort of a once and done cosmetic. So if you happen to miss the audio or you miss the montage playing, nothing in the world, it's sort of a stateless scenario, right? Nothing in the world has changed because I played this audio or I played this montage. If you were there and you heard it and saw it, great. If you weren't, no big deal. They're also unreliable. Both of them are unreliable because there are more important things to be replicating across the network than an audio file or a montage. You see this quite frequently in games when there might be a big battle and some of the visual effects are being dropped for performance reasons. That's done through this unreliable call because things that are stateful, things that affect the game experience, you want those to be reliable. But things like this, they don't need to be reliable, so they can be unreliable. We have the look at, which is just some basic math that when we give it a new point in the world, a new world location, this rotates the AI pawn to look at that location. And then we replicate that new target location to the clients. And so that little chunk of code, if you expand these and look at it, is where all the client server activity is occurring. There's a new nameplate component in this source code that's attached in the description below. There's 2 parts to it. There is the nameplate component, which is added to the AI pawn. And then within the nameplate component, there is a reference to the nameplate widget. And so the nameplate widget is just a child of the UMG widget. It allows us to expose certain functions in the component, such as hiding elements, changing values, etc. So there's two classes here, the component and the widget. And the most important function is in the component. And in the component, you'll see some logic called update floating nameplate. And what update floating nameplate is doing is it's testing the distance between the player and the AI and determining if the player is close enough to see the nameplate. So it basically hides the nameplate if the player is too far away. It also hides the nameplate if there's an obstruction between the visible channel between the player and the AI. So if the player and the AI are within distance, it'll do a line trace. If that line trace hits some other object in between, basically blocking visibility, then it won't show the nameplate. But if it does pass the test of distance and it passes the line trace that they can see each other, it will then configure and present the nameplate. It's just a way to not clutter up the world with useless nameplates all over the place. And it does have a nice sort of secondary effect of keeping your draw calls down. So you'll see that function. Feel free to scroll through that as well. It should be well documented. There's also a new AIPawn movement component. What we found, and if you look at the tick component logic in the AIPawn movement, you'll see how we're performing this. And what I'll do is I'll post a video. I'll cut and post here a video of it on and off so you can see what it's doing. But basically, because of the frequency at which the server sends data to the client, because they're using simulated proxies for the AIs, can look to be jumpy and staggering forward. So this smooths out the movement of the AIPawn on the client in between server updates. And so we'll show the video here in a minute with and without that, so you can see why that's important. So in summary, you've got two new components, the nameplate and the AIPawn. We dropped two components. We dropped the common conversation, which is in beta. It's a plugin by Epic, but it's not flushed out by any means of the imagination, but something you might want to watch as they continue to release releases. We dropped the sphere collision because we have not yet been using it, and it's just basically cluttering us up for no reason. And then we've been testing and adjusting our client server performance and look and feel. So those are the summaries in this release. Let's go look at some of this in the editor, and we'll try to show you some rationales why. But feel free to download the source code out of the description, explore it on your own, leave a like or a comment, and again, thanks for watching. Okay, in this recording, the blue team is running on the server, and the red team is my client. So this is my server window, and if I tab around, this is my client window. So what we're going to do is we're going to approach the spawner edge. What should happen is our AIs are going to spawn in, and as I get closer, you'll notice the nameplates over top of each of the actors. These nameplates, this one has the health bar. You see the health bar underneath the name. And these two are moving, and they're moving relatively smoothly on my client. This is because we are running the simulation. We will show a video clip in a moment where we've turned off the simulation, and you'll see the difference. But right now, note that they are moving generally smoothly on the red client viewport, and that if I move behind this, watch the nameplates, they will slowly disappear as I lose the line of sight trace to each of them. So you see the one appearing as I move from side to side. So that's showing the nameplate logic, again showing that these have no health bar, but these two actually have a health bar. And then we're seeing the animation running, which is the multicast, and the audio track, which is also on the multicast. So this is the final product on a client version. If we flip to the server and then move in, you'll see that everyone is already spawned in because our client is within the sphere, and everything sort of functions appropriately on the server as well, and they're tracking consistently. All right, so now what we're going to do is we'll stop, we'll turn off the synchronization, and we'll relaunch the clients, and you can see the difference between the simulation of the movement versus just allowing replication to move the AI actors. Okay, so now what we're going to do is we're actually going to comment out the simulation of the movement between server updates. So in our AIPawn movement class, in our tick component, we have this code, which you just saw running. And I'm going to go ahead and comment out all of the simulation and just allow the server code to run. So what we're going to do is, if I comment out all of this, which is the simulated proxy, but leave this in play, then we will see why we need this logic to simulate between server updates. Okay, so after compiling and packaging, we have launched both a server and a client. The blue Manny is the client, the red Manny is the server. And so what we're going to do is advance into the spawner range. And what you'll notice is that the move tos are very choppy. So note, we'll just leave it here for a moment. Sort of an extremely sort of choppy looking experience, right? Nothing good at all. Everything else seems to function just fine. However, sort of see them moving there, kind of jerking along. If I flip to the server, they're actually moving quite smoothly. So here you see them moving along. This character moving along. So on the server, they're moving quite smoothly. But on the client, they're not. And that's because the replication of the physical location is dependent upon a number of things like network frequency, etc., which is causing the movement to be staggering and jumpy between frames on the client. That's why we added the simulate, which basically simulates movement until such a time as the server sends back. It looks like I've got a really bad ping going on there. Yeah, so we've got some real network issues going on, which is probably why they're not moving at all. But even when they are moving, you'll notice that they're moving in a very erratic, choppy fashion versus on the server where they're moving quite smoothly. And that's because we're not simulating between net server updates in this build right now. Okay, so now I've re-enabled our simulated proxy of simulating movements between steps to fix our jittery. And what I want to do is show the difference between the behavior tree as the default intelligence for our AI and the script definition. And so what I've done is these are all running the behavior tree, and I've just basically copied the exact same move to location node multiple times across the screen. That's giving us a bunch of actors that are going to be executing through their behavior trees, and we should be able to get a gauge of overall performance. So I'm going to go ahead and package this, and then we'll run it in a game client, and then I'll come back, repackage all of this as a script version, and we'll run it, and we'll see if we see a performance delta between the two of them. Okay, so we've compiled and packaged the behavior tree example where we get into range where more and more of them are coming into play. And what we're really interested in is the game thread. So you can see my game thread is running maybe 8 milliseconds, standing here, 7, 8 milliseconds. And as I move around, the game thread might be 9. It's basically bouncing between low 7. I saw a 10 there. Mostly in the 7s and 8 milliseconds. Now we should be ignoring the draw call, the GPU call. We're really only looking at the game thread because the game thread is what's processing the script versus the behavior tree, and whether or not we're drawing 5 actors or 6 actors, it's going to be consistent in either of the two. So what we're really trying to look at is the game thread, which appears to be running around 7 with the behavior tree, with some 8s, 9s, and 10s. So 7, 8, 9, 10. I don't think I've seen a 6 as I've moved around this area. I've seen lots of 8s and 9s. And again, you can watch the video yourself. But basically, I would say mostly 8s if I were to make a judgment call. with some 9s. You can see it got a little higher there. Yeah, I would say mostly 8s. And I move around this this general mob of behavior trees. Moving, you might even say 9, but I would say 8. All right, so that's the performance criteria of the behavior trees running. Now let's go switch them all out to the script definition model, doing the exact same movements, and see if we get a performance improvement. Okay, and now the same experiment with the script definition. So you'll notice that each of the characters has the SD prefix in front of all their actions. And so they are running around now using script definition as opposed to behavior trees. And I see 7s and 8s. I'd say not as many 10s, although an odd one pops in every once in a while. Mostly when I move dramatically. So I'm going to have to study these side by side to see the millisecond variance. And are we actually picking up enough performance improvement? I got to run them side by side. I would say this is more performant. I saw some 6s. It's definitely staying in the 7s more frequently than it is the behavior tree. It might be a little more stable. But it's definitely showing that both at scale are not hitting high performance issues. So whether we behavior tree or script, at least at the minimum, they're going to be equal in performance. I'd have to play this back at slow-mo to see if one is more efficient than the other. But the original intent of the scripting was to make it easier to configure repeatable characters in world. And so being the moving component being the most expensive, it looks like they're equal. And of course, if they're stationary without the behavior tree, they should be more performant. So hopefully that's helpful. And feel free to download the code, take a look at the logic, leave a like, a comment, a challenge in the notes, and we'll try to keep improving it. Thanks for watching.